This is lecture number 1 for module 4 in the book Problem-Solving Guide for Electromagnetism and Optics. This lecture is on capacitors. A model for a capacitor is two parallel plates, like this. Put some leads on them so they can be part of a circuit. You can hook things up across them. Capacitors have many functions, one of which is to store energy and provide a sharp burst, like the flash of a camera. So you might hear the capacitor charging if you have an old camera. And then it's charged, and then you press the button, poof, and you get a big flash. A defibrillator will give a big jolt. You charge up the defibrillator, and then you connect these ends. This one goes on one side of the person's chest, this goes on the other side, and bam, the charge will run across. The energy burst is provided by separating charge. There's no net charge here. Just force the electrons from one side to the other. You pulled them off of this side and stuck them over here with a battery or a power supply. And if you allow them to come together suddenly, that's a sharp burst of energy. Capacitors are basically buckets to store potential energy, electric potential energy, by separating charge. It's somewhat similar to pulling back a bow in a bow and arrow, where you pull it back slowly, get a lot of energy stored, and then bam, release it all at once. Or, for example, pulling a spring. Pulling a spring, cranking it open, and then launching something. The capacitance of a capacitor is the magnitude of the charge it's separated divided by the voltage between the plates, like this. This Q is the magnitude of the charge. When they say a capacitor is charged, it doesn't mean that it has a net charge. It means it has a charge separation. The net charge is 0. The charge wants to be together, but we force it separate to store energy. We can use Gauss's law to show that the capacitance is only a function of the geometry of the capacitor. The electric field inside a capacitor is the voltage difference divided by the distance between the plates, V over D. Gauss's law, E dot A is 4 pi kq enclosed. If we enclose one of the plates, the field lines are only from the positive to the negative. So we only have the area of this side, which is the area of the plate, and Q enclosed is the total charge on the plate. The electric field is V over D. I can solve for the voltage and get this expression. And then I can stick it into the equation for the capacitance, Q over V. This A is in the bottom up here, goes in the top. I cancel the Q's, and I get this constant times A over D. So the capacitance of a capacitor is the area divided by the distance, directly proportional to the area of the plates, inversely proportional to the separation between the plates. So let's think about the capacitance of a capacitor. Here's two capacitors. The distance, they have the same area. The distance between the plates, this one is twice as big. If I connect a battery, identical battery, like that, to charge up the plates, which, if either, will separate the most charge? Pause the video and think about this. Think. What does voltage mean? Okay, the voltage drop across each capacitor is the same, and it's the voltage across the battery. If the battery is 12 volts, the voltage drop across this gap is 12 volts. The voltage drop across this gap is 12 volts. The voltage drop is the energy a charged particle gets as it falls from one to the other. So if we release a positive charge at the positive plate and it falls to the negative plate, it should get there with the same energy, because the voltage drop is the change in kinetic energy divided by the charge. If it has the same mass and the same charge, it should hit the negative plate with the same kinetic energy. But these two plates are closer together. The particle has to accelerate faster. It doesn't have as much distance to get up to the speed. So the acceleration is bigger, the force must be bigger, which means the field must be bigger. And if the field must be bigger, it has to have more charge. This is how it looks. The charge on this plate is twice as big as the charge on that plate. So even though the area is the same, the capacitance is bigger because this capacitor will hold more charge for a given voltage. And this is consistent with the equation C is a constant times A over D. The smaller the D is, the bigger the capacitance. Before we go any further, let's talk about SI units. So the equation is C over V, which means the unit of capacitance is Coulomb per volt. Coulomb per volt. And it might be a good idea to just call it Coulomb per volt. Then you might know what a capacitance is. But like the volt, which is a joule per coulomb, the unit of a capacitance has been given a name. After Michael Faraday, it's called a farad. So a Coulomb per volt is a farad. And like the Coulomb, a farad is a very large capacitance. So when you talk about a capacitor in a circuit, we usually use micro, millifarads. So this module, we're going to be looking at complicated circuits, and we're going to have to calculate the voltage across the capacitor, the charge on the capacitor, maybe even the capacitance of an unknown capacitor. Let's start with one battery and one capacitor and think about what's going to happen, what's going on. When you connect the battery, it pulls electrons off this plate and puts them over here, like this. Electrons are missing from this side, and they're over here. This charge has to be equal to that charge. If you're going to use a voltmeter to measure the voltage difference, any point on the right side is 12 volts different than any point on the left side. It doesn't have to be on the plate. Here, if you can stick a voltmeter on the wires, it's going to read 12 volts. Here, the voltage difference between these 2 points is 12 volts. On the plates, 12 volts. Now let's consider two capacitors in series. We're going to give them the same capacitance. What's going to happen here? The battery thinks there's only one capacitor up there. The battery does the same thing it always does. The battery takes charge from one side of the plate and puts it on the other side. The battery has no connection to the inner plates. The only thing the battery knows about is this plate and that plate. So the battery pulls electrons from this plate, which it's connected to, and puts them over here, which it's connected to, like that. Now let's consider the inner plates. What's going to happen here? Metal, it's full of electrons, and they're free to move. That's what a conductor is. So this side has got electrons on it, and electrons are repelled by these electrons, and they're attracted by this positive charge over here. So the electrons in this plate are going to run over here, and they're going to want to go all the way to the positive, but they're going to hit a dead end. They're going to dead end in this plate. And when the electrons leave, this becomes positive, like this. So we come to an important conclusion here. Capacitors in series must have the same charge. Of course they must have the same charge. The electrons that are here came from over here. If this is 3 nanocoulombs of electrons, this has a deficit of 3 nanocoulombs of electrons, which means it's positive 3 nanocoulombs. The electrons that were here came from over here. There's no net charge anywhere. Capacitors in series must have the same charge. There's not a rule to remember. You should never be saying, I can never remember what the rule is. Is it same charge or same voltage? I can never remember. It's a concept to understand. The electrons are real entities. They move. There's no frickin' way this charge can be different than that charge. It doesn't make any sense. It should make sense to you. Don't remember the rules. Remember the concepts. So the battery treats the circuit as a single capacitor. So let's calculate the equivalent capacitance. That's the capacitance the battery thinks is up there. Going to replace the whole circuit with one capacitor. And we're going to do it generally. We're not going to use the same capacitance. Two capacitors that are not the same. Got a small one and a big one. What happens here? Which one gets the bigger charge? Which one, if either, gets the bigger charge? Think about that. I have a battery connected in series with a small capacitor and a big capacitor. Which capacitor gets more charge? If you said they're different, go back to the last slide. They have to be the same. The battery pulls electrons from here and puts them over here. So the equation is the same capacitance equation, but this is the equivalent capacitance of the entire circuit. Q is the charge that goes through the battery, the charge that's shuttled through the battery from one side to the other. And V is the voltage of the battery. So this is the capacitance of the entire circuit, the single capacitance of the entire circuit. So this is what happens. This charge is equal to that charge, this charge is equal to that too, the magnitudes are all equal. The charge that goes to the battery is also this charge, because there's only one capacitor that can take the charge from the battery. For each individual capacitor, we have the same equation, C is Q over V, but this V is the voltage across the capacitor. This is the charge on the capacitor. This is the capacitance of the capacitor. This is not the voltage of the battery. If you like to plug things into equations without thinking, you might plug in the voltage of the battery here and get the wrong answer. So you can think about it as this. The capacitance of capacitor 1 equals the charge on capacitor 1 divided by the voltage across capacitor 1. Same thing with capacitor 2. It's true for every individual capacitance in the circuit. And if you want to use the equation for equivalent capacitance, you have to use the charge through the battery and the voltage of the battery. So we understand fundamentally that the charge has to be the same. These capacitors cannot possibly have different charge because the charge one has came from the other capacitor. No charge comes from the battery. The battery is not a source of charge, it's a charge pump. It pumps charge from one side to the other. If the charges are the same, the voltage drops can't be the same. Look at the field lines here, they're far apart. This one has a much bigger field. This has a lot more storage capacity, but it has to have the same charge as this one. If you go across this capacitor, you're going to get a bigger kick from the field. So therefore, the voltage drop across this capacitor is bigger. We know that the total voltage drop has to be the voltage of the battery. So the voltage of the battery is the voltage drop across this one plus the voltage drop across this one. For capacitor 1, C1 is Q1 over V1. For capacitor number 2, CQ is Q2 over V2, but the charges are the same. We don't need to have subscripts on them. There's no difference between Q1 and Q2. They have to be the same. So we can drop the subscripts. We can write this. These Q's are the same. And it's also Q through the battery. We can solve this for the voltage drops across the capacitor by switching the V's and the C's. And we know that V1 plus V2 is the voltage of the battery. If this is going too fast, just pause it. So now we can substitute this expression into our expression for the entire circuit, which is C equivalent is Q over V, and this is V, right there, V1 plus V2. Stick that in for V, cancel the Q's, take the inverse of both sides, and we get this expression for two capacitors in series. The equivalent capacitance of two capacitors in series, one after another, is 1 over C1 plus 1 over C2, and that's 1 over C equivalent. Let's see how this works. Let's plug in some numbers. Two 60 microfarad capacitors in series, like that, back to back, one after another. C equivalent is 1 over C1 plus 1 over C2. C1 and C2 are both 60. 1/60th plus 1/60th is 2/60ths. 2/60ths is the same as 1/30th, and 1/30th is 1 over C equivalent, so C equivalent is 30 microfarads. We added a second capacitor, which stores charge, and now the capacitance went down? What the heck? How did that happen? We have a 60 microfarad capacitor, and we say, I'm going to store more charge. Let's put another capacitor in there. Let's put 2 in there. And now we can only store half as much charge. We have to understand why this is. Well, now each capacitor has half the voltage drop that it had before. It can only store half the charge. It's the same capacitance individually. So let's put some numbers in here to see what's going on. Battery voltage, 12 volts. Capacitors, 60 microfarads. What happens here? Each individual capacitor will have a voltage drop of 6 volts across it, so we can calculate the charge on this capacitor right here. We know it's got a voltage drop of 6 volts across it, and we know it has a capacitance of 60 microfarads. So we plug in the numbers, and we solve for Q, 360. So this Q has negative 360 microcoulombs on this side, positive 360 on this side, and so does this one. The battery thinks there's a 30 up here. This plate and this plate combine to be 30. And we can use C equivalent to calculate the charge through the battery. This is the charge through the battery. That's the voltage of the battery. The charge through the battery is 12 volts times 30 microfarads, which is 360 microcoulombs. And that's what we got for the charge on this thing. So it all fits. The battery pulled 360 microcoulombs from one side to the other. The battery thinks there's a 30 microfarad capacitor up there. It all fits. It makes sense. Eventually, maybe. So each has a voltage drop of 6 volts across it. Each has 360 microcoulombs of charge separated. If we only had one 60 microfarad capacitor across a 12-volt battery, it would separate 720 microcoulombs of charge. Twice as much charge. This is better. This stores more charge. If you add another capacitor in series, it reduces the capacitance and you store less charge. In lecture 2, we're going to see how to connect 2 capacitors in a circuit so that capacitance goes up, which is, sort of what you want to do.